My name is Hunter, and this is content review for general chemistry students at Portland State University. Today we're doing chapter 12 and going over some kinetics and an introduction to rate law. So this will be a pretty short one, and I'm delivering it early so that I can attend an event tomorrow. So you will all be watching this in the future, either on the PSU Learning Center YouTube channel or on the Twitch stream right here. So first problem, number 6, consider the following reaction in aqueous solution. If the rate of disappearance of bromide ions in aqueous solution at a particular moment during the reaction is 3.5 times 10 to the negative 4 moles per liter, moles inverse liters, per second. What is the rate of appearance of bromine, diatomic bromine, at that moment? Because we're given a balanced chemical equation here, we can simply use the stoichiometric coefficients, 5 and 3 rather, as a conversion factor. And I really like to run this as a dimensional analysis and looking at my species as units rather than trying to think too hard about rate laws. So simply put, we're given that at a moment in time, the rate of disappearance of bromide ions is 3.5 times 10 to the negative 4. And I'm going to use bromide as my unit. We know that for every 5 bromide ions that disappear, we have 3 diatomic bromines, which is what we're trying to get to, that appear. And we can simply run this now, where our bromides will cancel out, and the units that we are left with is diatomic bromine. So we take 3.5 times 10 to the negative 4, multiply it by 3, divide it by 5, and that gives us a final answer of 2.1 times 10 to the negative 4 diatomic bromine that are appearing. So that is the rate of appearance for bromine in this reaction. I like this example because it's taking a new concept, which is this reaction rate and kinetics of a reaction, and putting it in terms of something that we've already done a lot of, which is just converting units, right? All right, next question. Describe the effect of each of the following on the rate of the reaction of magnesium metal with a solution of hydrochloric acid. The molarity of the hydrochloric acid, the temperature of the solution, and the size of the pieces of the magnesium. This is one where I feel like it's important to visualize it. So we have some container, we have some mass of magnesium metal, and then we have an aqueous solution with our hydrochloric acid floating around in there. So if we increase the concentration of hydrochloric acid, what is that going to do to the reaction rate? Thinking of this just really conceptually, we have hydrochloric acid, hydrogen dissociated from chloride in water. If we increase the number of free hydrogens and free chlorides, more of those are going to be available to bump into the magnesium and react with it. And so that should move things along faster, right? This is just simple collisions. So this would increase the rate. If we increase the temperature, thinking about the definition of temperature, right? Temperature is simply a measure of the average kinetic energy of a system. And so if we increase the temperature, we add energy to that system, maybe with a heat source, we excite all of those hydrogen and chlorides and they move around a lot faster, which is also going to speed up how many times they collide with the magnesium metal per unit time. So this is also going to increase the rate. Now, if we increase the size of the pieces of magnesium, I want to make sure I read the question correctly here. Describe the effect of each of the following on the rate of the reaction. So if we increased the size of the pieces of magnesium, right, let's say we keep the mass or we keep the number of moles of magnesium the same, and we just change the number of different parts. Or this that language was confusing. If I have one piece of magnesium that consists of 1 mole versus two pieces that combined equal 1 mole. We have 1 cup here, and that's a different cup. Which one is going to react faster? This one might be a little tricky, but for me thinking about this, um, it's simply about surface area, right? If you have many small pieces, um, or if you have more surface area around the material for the hydrogen chlorides to collide with, then you're going to have more collisions and you're going to have a faster reaction. If you take all of your material and you put it into one super chunk, you're only able to access the material that's around the perimeter, just the external surface area, and not the atoms that are in the middle of that chunk of metal. And so your reaction rate is going to be much slower. So increasing the size of the chunks of magnesium, assuming you have the same amount of magnesium, is going to decrease your rate. So conversely, many small pieces would result in a increased rate or a faster rate. Okay. Tripling the concentration of a reactant increases the rate of reaction 9-fold, so 9 times. With this knowledge, answer the following questions. What is the order of the reaction with respect to that reactant? And increasing the concentration of a reactant by a factor of 4 increases the rate of reaction 4-fold. What is the order of the reaction with respect to that reactant? So I've written sort of a generic rate law up here on the top right, where K is your rate constant, and then you have concentration of reactant A to some exponent M, concentration of reactant B to some exponent N. When we're looking at a single species, you can write this simply at looking at a single species. If doubling, or excuse me, what did they say, tripling? Tripling the concentration of A resulted in a 9-fold increase, what times 3, or 3 to what exponent rather, gets you to 9? 3 to the 2 exponent. So M must equal 3, or sorry, M must equal 2, because 3 squared equals 9. And so the order of the reaction is always the sum of the exponents that we kind of talked about. We're only looking at one species, so we only look at that number 2. So this is a second order reaction, or you could just simply write the number 2. Increasing the concentration of a reactant by a factor of 4 increases the rate of reaction 4-fold. What is the order of the reaction with respect to that reactant? So that reactant, we quadrupled the concentration of reactant. The rate increased by that same factor, and so that would be a first order. Or you could simply write the number 1. Okay, don't overthink that one. This is kind of neat. Radioactive phosphorus is used in the study of biochemical reaction mechanisms because phosphorus atoms are components of many biochemical molecules. ATP, adenosine triphosphate, right? The location of the phosphorus and the location of the molecule it is bound in can be detected from the electrons or beta particles it produces. And we're given a balanced equation here and a rate. So what is the instantaneous rate of production of electrons? Production of electrons in a sample with a phosphorus concentration of 0.0033 molar. Well, this is great. We're already given a rate, or excuse me, we're given our K, we're given our K constant equals 4.85 times 10 to the negative 2. That is, well, per day, per concentration of phosphorus. So we see that looking at our balanced equation, there are no stoichiometric coefficients. So we should be able to just write this out times 10 to the negative 2 times our concentration of phosphorus, which would give us 1.6 times 10 to the negative 4 instantaneous rate of production. Yeah, per day. Cool. All right, question 25. Nitrogen monoxide reacts with chlorine according to the following balanced equation. The following initial rates of reaction have been observed for certain reactant concentrations. So we have our different species up at top, and then varying concentrations in our different rows. What is the rate law that describes the rate's dependence on the concentration of NO and Cl2? What is the rate constant, and what are the orders with respect to each constant? So looking at this, we have equal concentrations, and then we have a rate that corresponds with that. Going down to the next one, we've doubled just the nitrogen monoxide concentration, and that has done more than double the rate. So we know that this can't be a first order reaction because there's some exponential relationship. Now, if we hold that concentration the same and we double the concentration of chloride, now we seem to have what appears to be a doubling. So it looks like the order of reaction for chloride is first order. How do I want to write this? Yeah, so first order for the chlorine, rather, not chloride. And we have what looks like an exponential relationship with the nitrogen monoxide. So that'll be second order for nitrogen monoxide. And then that gives us the basis for calculating a rate. So if your numbers looked a little more complicated than this, you could plug it into this new equation now that we know the order of the reaction with respect to each reactant. But because they were so kind as to give us concentrations of 1 mole per liter for um, each of our reactants, we're actually given the answer right here, which is 9.12. So K equals 9.12. And if you want to run that, your units will be liters squared inverse mole squared inverse hours. Yeah. Oop, come on. There's K. There's your rate. Second order, first order. And last one. Question 31. The following data have been determined for the reaction of, looks like iodide with OCl. So this is a simple exchange reaction, it looks like. We're removing an oxygen from the chlorine to the iodine. Determine the rate law and the rate constant for this reaction. So we have this table set up a little bit differently. We have initial concentrations and we're given rates. Okay. So, and then it looks like we have trials 1, 2, and 3. So we have a simple increase by a tenth, 1/10 molar for iodine for each of these, and a corresponding increase in the rate. And we held the concentration constant here. And it appears, so that was a doubling of the iodine concentration. We have what appears to be a doubling of the rate. So I'm going to go ahead and say first order for iodine. And then we don't have a really clean, like we've obviously changed our concentration in iodine from trials 2 to 3, but we have a really dramatic decrease in concentration for OCl between trials 2 and 3. And we have a corresponding decrease, but it isn't 1/5. It's almost 1/5 because we increased this, so that's kind of balancing it out. But it doesn't appear to be an exponential relationship, right? This looks like it's pretty direct. So I'm going to make an educated guess and say that this is first order for OCl, right? If we simply divided 6.2 times 10 to the negative 4 by 5, we would get something close to 1 times 10 to the negative 4. So there's no drastic change there, which gives me the impression that it's a first order reaction with respect to that reactant. So now we can create a rate law based on that, where the rate equals K times the concentration of iodine times the concentration of OCl, and we're actually given a rate. So let's go ahead and pick any one of these and start here. Excuse me. 3.05 times 10 to the negative 4 equals K times concentration of iodine times concentration of OCl. Do some algebra to get K by itself. And that gives us 0.061. And our units are in moles per liter times second, which can also be written as it is up here. And we're good scientists, so we're going to do it in scientific notation. 6.1 times 10 to the negative 2 liters, excuse me, moles, inverse liters, inverse seconds. All right. I hope that was helpful. Again, you can find these recordings on the PSU Learning Center YouTube channel. I will see you next week. Enjoy the longer days. Get some sunshine on your eyeballs this weekend. Be well.